All right, I think we're live. Let me know in the chat if my audio is fine. And once I get confirmation, we will hop straight into things. I don't think I need these headphones. All right. We've got both Joao, C4 Tubo. Maybe we should shout out the YouTube channel. Proglang Base, I believe, is the YouTube channel, which C4 Tubo in the chat is one of the hosts of. So the last two episodes have been on APL and BQN. So I guess we can link this. If you're interested in these kinds of videos, you're probably interested in, in these kinds of live streams. You'll probably be interested in this YouTube channel. Check it out. And yes, another Jello live stream. What is the 30-second summary for those of you that might be tuning in for the first time? Jello is a Python wrapper, originally around the Jelly array programming language. But since then, we've forked Jelly, and we've added a number of primitives, and we've made a couple changes. And this is just, originally this started out as a tool to kind of demystify the Jelly language, because everything in yellow here is basically atoms, is what they call them in the Jelly programming language. And so Jello adds keywords, one keyword for every atom, and basically it's an explainer tool. Ideally, this iota flat less than prior, dyadic separator plus multiplies, right, monadic separator, scan, maxr, add one. Even if that's not readable, hopefully it is more readable than the yellow atoms. And we've been, I think, we've done 5 live streams, so this is live stream number 6. And hopefully we're going to get to something that's going to be pretty exciting. And I think I actually have, let's get the to-do list. So I've opened a number of issues over the last couple of days. Saki says, love your videos. Thank you. And have you considered making a video on combinators in Haskell? I have not. I have considered making a video. I got to take this off of full screen because I can't. Actually, let's go to combinatory logic, links. Weewa recently added a combinator documentation page with similar diagrams. If we go back and we look at the ones from, sorry about I gotta turn this into dark mode at some point. We will do that. If you go to the BQN combinators page, you always see these diagrams that explain things. So I have thought about making a YouTube video going through these and comparing these. I kind of already have a video. I mean, that's what's on the main page here, the composition intuition. I don't really talk about Haskell in this video a lot, but I mean, at some point I go through, like, from minute 33 to minute 40 something. Anyways, it's not comprehensively going through one by one in Haskell, but there are videos out there. How do we share this if people yes. Anyway, so maybe in the future I will do something like that. But let's close some of these, close this, and close this as well. Anyways, we are back to our to-do list. So I've actually already done this one. We're just going to commit it, and I'll go through it. And then we're going to take a look at a problem that we looked at in the last live stream, solve it in a few different languages. Then we're going to go through and implement and organize all of the splitting, cutting, partitioning functions and filtering functions. Then we're going to come back to this problem, which requires keep, is what Weewa calls it. And once we've done all this, hopefully, what is it now? It's 5 p.m. local time. I'm hoping we can get this all done in like 2 or 3 hours. And then I want to implement this find the algorithm, which will be like a automatic way of just giving an input and output, and then it's going to generate you a bunch of solutions, which was recommended by someone. This kind of already exists in a programming language called Pharo. It's like the most modern implementation of Smalltalk. And we're probably not going to get to 27, which is implementing some convenience functions, but C4 Tubo saying he rewatched the composition intuition talk. But anyways, let's go through. So if we go to issues here, oh, that's on Jellyfish. If we go to the Jello issues, if I can click these correctly, the first one, which like I've said, I've already done, is in this one that we're going to look at in a second. This investigate Perl Weekly Challenge 258, which is this problem. Part 2, it says some values. This is actually a leak code problem that they stole. And it says, given a list of integers and a value k, count the number of 1 bits in the binary representation of each of these integers, and then sum up the ones that have k 1 bits set. So, I mean, this function, I actually asked ChatGPT this earlier, and typically languages call this like bit count or pop count. Some language, I think C# calls it ones count. And let's go quickly to, I mean, I already have it here, right? So here's our list, 259.11.3. I changed 1 to 2, and it's actually, it's not the integer itself, it's the corresponding index. So first we want to get the corresponding index. That's len iota 0. And then we want to, initially we were doing this, I to b, which is going to convert our integer to a binary number. And then we get these binary representations. And then we want to sum across each of these sort of binary representations to get the bit count or pop count. But you can see now, I've got this little algorithm advisor that says I can replace I to b sum with bits, which is my name for bit count or pop count, because bit count and pop count are too long. So now if I replace this with bits each, it now is basically going to do that sum automatically. And then this is where it gets tricky. I guess I did figure out, you know, if we go back to investigate, whenever you have a dyadic expression and you need to refer to only the left or right argument at certain points in times, it gets very tricky. I think I figured it out, because now what we want to do is we want to apply equals to this list of bit counts to just the right argument to see which of these are equal to the k number of bits set. And if we do equals r, that works. So you see k is equal to 2 here, and the only 2 is now equal to 1. And if we change this back to 1, all of the ones, so 1, 1, 1, we're going to get 3 ones now, are equal. So this is fine, but we're still missing the keep function. And anyways, if we want to go and take a look at how did we implement bits in my Jellyfish repo, which is the fork of Jello, we can just do a git diff. Basically, I added a README that says, you know, we've added this bits function. I chose this Unicode 1 in a circle, because I don't know, it's kind of looks like, you know, a bit count thing, and all the B's were taken. And you can see here I've added this little Unicode 1 to the list of glyphs. And if we keep on going down, I basically went and found the piece of code that links to sum, which is just this thing. And all I did, actually, let's go actually look at the source. So if we come, put this here, and we go back here. So if we look for reduce, or is it functools.reduce? How many times do you think? So 7 times. So that's the one I added. This one, it's not P, so S. Basically, S is the corresponding atom in Jelly for sum, and this is the piece of code that invokes it. And basically, all I did is I copy and pasted this and replaced this Z, which is the list, with, if we go up, so this is the piece of code that I added. I replaced this Z with just like wrapping it with a to base, which is what does our to binary representation conversion. And then I got rid of that little if list else sort of error check thing. And it basically works. And then once you do that, you just have to recompile this. So now let's commit this. Actually, we always got to remember my screen, my very bottom of my screen doesn't show. So I always got to remember to clear when we're at the bottom. We go sparkles, add one for bits. And we don't need to close any issue here. And we can just push that. We've already built this, so we go back to Jello now. And the changes we've made here are just basically in the algorithm advisements. We've added this I to B sum equals bits. And then in our tokens, Monadics tokens dictionary, we've just added this, bits keyword to correspond to our bits atom. So we can once again go git add, git status, git commit, sparkles, add bits for that. And if we come back to Opera, add bits, this is going to close this issue. We're done that. We come back here. This is closed. Fantastic. So we're one issue down. How do I get a little emoji check mark? Yeah, let's copy and paste this thing. And we can come back here and mark that done. So I haven't read the chat in a second. I'll have to check out the Weavos Combinators page. Yes, it's pretty cool. I see you added even, which isn't Jelly's convention to use uppercase letters for monads. Oh, I didn't even realize that. That was the convention. Huh. So let's if that's the case, let's go to. Have I messed that up then too? What is So what is the convention? Uppercase. Let's go to the that site. Come back here. So monads are uppercase, dyads are lowercase, and higher order functions, aka quicks, are whatever you want. So let's see how badly I've messed that up. I guess prior doesn't really matter because it's a higher order function. This is a symbol, so it doesn't really matter, but this should be. So yeah, let's go to shape catcher and see if we can get accented uppercase. Wow, come on. Woo. Recognize. There we go. And I'm pretty sure that's not being used. Yeah, so let's replace. And also, then we'll put this back because I think we stole this from here. And then we also need to go copy this and go %2. And we need to change this. Come back here, get status, get diff. We didn't update the README. And now we need to install this, switch back here, and we need to go to tokens and find where even is. Yeah, I guess I should have noticed that. And now, if we type something that uses even, it should still work, which it does. And now you can see here that the atom. So thank you to BR Panic for pointing that out. And let's go commit all this stuff. So yeah, we updated the README. we put back the lowercase e and we did all the substitutions. So git status, git add, recycle, change. I guess we kind of need and we need to go back here to get this lowercase e overdot. And maybe we'll put in parentheses, it is a monad. And we come back here. And we can go git add. We can use the same commit message. All right, we're done that. Echo says, I prefer the power on. Whoa, what does that mean? And BR Panic said that there does look like there. Well, so maybe that whole refactoring wasn't necessary because there are lowercase. Okay, maybe that was an unnecessary 5 minutes of work, but only in the OE and AE. Yeah, but why are these, separate? They just ran out of letters. Who knows? There's probably a method to the madness. Anyway, so we're done now. Our to-do list here. So let's go back to this. To this problem now. So we kind of solved it a little bit. We solved it a little bit here. And now what we need to do is we just need to, well, actually, I don't even know, because once again, so now we have our mask, but we want to apply our mask. We want to apply our mask just to the left argument, which actually works. Well, look at that. That's actually beautiful. I mean, what am I talking about? Yeah, because we don't even need to keep. So I don't even need keep for this function. So actually, I mean, I don't know why I was so worked up before. Whenever you need to refer to left or right arguments, it's really not that bad. You just use the R and L, which are like the K and the pi combinators or K and KI combinators. They just like discard one of the two arguments. So these are like binary functions. I mean, if we can go to combinatoriallogic.com again, go back to the table. So I think I renamed this pi. At one point, I think I called it kappa, but then we could call it pi because then it can be the penguin bird. Because that's the thing, in these combinatorial logic tables, ki never gets its own combinator, and therefore it never gets its own bird name, which is kind of irritating. So it's just these two combinators. Yeah, left tack and right tack and the APLs and such, and BQNs. So I guess we can just close this. I mean, I said we were going to solve it in Weewa because it's still kind of cute to look at how nice it is in Weewa versus APL. I actually haven't solved it in BQN yet. So yeah, let's do that. Well, actually, first things first, we have the solution. So let's just go commit this to our challenges. And did I actually put in PWC? Yeah, I haven't put it in. Come back here in a sec. And this is 258 P2. And the Jellyfish solution is that. Technically, we can copy this, put this here, and then we just need to go back to Pro Weekly Challenge, copy this, change that, and let's see if we can go find the leak code. Leak code, sum of values with binary. I mean, that should be enough. Yeah, there it is. Honestly, Pro Weekly Challenge just constantly stealing. Yeah, you're given a zero-indexed integer array. Return an integer that denotes the sum of the elements whose corresponding indices. Yeah, this is exactly it. So we go put that next to here. Is this the, yeah, that's that. This is 2859. So put that here. And that was not exactly what we wanted, was it? Open the preview. Oh, except we got 2 tasks in there. Whoops. So we got the links to all these. We got the solutions. That kind of looks funky, but I don't really care about the Jellyfish. The Jellyfish is just a back end for Jello. And yeah, I think that's all there is to do for this. So let's come back here. What do we do? This is sparkles. We don't really care. And this is solution to PWC 258 P2 closes this. Perfect. Look at that. We're 2 down, and we're only 25 minutes in. The stream is well, much more productive in terms of changing this. And I think I said come back once I have keep, but I don't actually need this anymore because I was just able to. Although actually, this is technically we need a. What do we need? We need a yellow circle emoji. We still got to go implement this because I said we would. So let's go do that. So first, let's go to wewa.org pad. And so what was our example? Two 259.11.3. 259.11.3. And we do that. So the first thing we want to do is we want to do length. We'll come back and duplicate this later. Then we need range. It's 0 index, which is what we want. Wewa very beautifully has the bits function, which is fantastic. A little bit off the screen right now. Actually, let's just do that. Zoom back in. Oh, except that's too much now because. And we want to do a row-wise plus reduction. And now we want to, now we just want to do this, right? Equals And now, nope. We want to, what do we want to do here? We want to duplicate. So what did we have? We had this. If we duplicate this, let's read the chat. Make sure power on has the 0 and 1 together. Oh yeah, I see that. I wouldn't say C4 Tubo is saying looks like I'm the maintainer of Jelly. Not really, because I'm not pushing anything to Jelly. And I think the goals of Jelly were to be code golf, and I have 0 goals to be a code golf language. I just really like the combinator model, and I like the plethora of functions that are not limited to a set of glyphs. I can just, every time I want something, I can just go implement it. So I guess I kind of want to do like a dip flip. Can you do a dip flip? Oh, you can do a dip flip. Is that necessary? I don't really know if that's necessary, but then we put all this back, and then we can just do what is it? Multiplication and then sum. I mean, that's definitely correct. I don't know if this is like extra though. If you can do this like this 3 characters, I'm sure it could be simplified. I'm not a Weewa expert. I don't spend enough time Weewaing. I will leave it to the chat. How can I what is that? Copied? Does that work? Like that. Here, I'll drop it in the chat. If folks want to tell me that there's a better way to do this. And so this is actually it's actually pretty nice. Minus that you got to do a dip flip duplicate. Which probably there's a nicer way to do this, but everything after that is beautiful, absolutely gorgeous. I kind of want to put it somewhere now. Let's put it in the challenges for now. Maybe I'll move it later. I'm definitely going to make a YouTube video on this problem though, because like I mentioned before, when you've got this problem where you need to refer to arguments at different points in time in your OG array languages, it's very tricky. And we'll see that in a sec when I solve this in APO. I was working on it earlier, and I didn't even get the full point free thing working. But let's just put a little subsection exploration of number 10. This is the solution in Weewa. Nope. Actually, should we just name this? What do we call this? Value sum? And then this is the solution. Actually, these are solutions in various other array languages. And then we'll go, yeah, I changed my mind, folks. Well, actually, how do we want to do this? Yeah, language. Actually, yeah, and explicit solution, tacit solution. And the first one is Weewa. Explicit doesn't exist because there's no such thing. And then if we go to preview and we skip down to the bottom, we got this. And then we just got to delete this. Very well, I got to delete that. Very nice. So next, let's do dialog APL. I mean, so the explicit solution, so I'm in ride here. Actually, let's start from scratch. Let's start from scratch. So we had what, 1, and then what was it, 2, 3, 5, 9, 11, 11, 3, or is it something like that? That looks right. And then we have alpha and omega. And just in case people are interested or they're always asking, how do I get boxing? It's boxing on. And it was on before, but by default it's set to off. So I've got this. So we don't have a bits function. Well, actually, first things first, we need what? We need the length. So that's that of the right argument, which is omega. Then we need iota. And then we need to add -1 or subtract by 1 because it's a 1-index language. And I guess, can you guys always see this? I'll keep on trying to scroll up. Just actually, we can skip out of full screen to give us a little bit more. There we go. And then after this, we want to do the equivalent of bits. And there's no bits function, so we have to do, if I'm mistaken, a inverse to decode. I think it's decode. I can never remember if it's decode or encode. And then we do an inverse with another -1, but we need to do this. And I think we need a tack here as well. Yeah, there we go. And now we need to do, so this is basically in the columns, the binary representations of 0, 1, 2, 3, 4, which makes sense. Then we need to do a column-wise reduction. And now we need to bring in our alpha, our left argument, check if it's equal. Then we need to do multiplication with our right argument, which is omega. And now we just do our plus equals. So, I mean, not bad. Minus, this is too bad that you have to do that. Create a fork. Is that a fork? Yeah, it's a fork. An AGH fork or whatever you call it. Anyway, so that's our explicit dialog APL solution. But now let's try and make this tacit. And this is like an uphill battle, even for like a combinator expert, if I do say so myself. So the best way I find to do this stuff is like simplify your expression for the moment, because we can definitely make this tacit super easily. So let's put some parentheses around this. We're going to get rid of those at the end of the day if we copy and paste this over here. And we get rid of our omega. So first thing, there are a couple things we can do. We could put the right tack here. But I don't want to do that. So if we just turn this using the B combinator on a top, because these are both unary functions. So this is a monadic application of a top, which is the B combinator. So this turns this unary function, these two unary functions, into another unary function. And then we have unary function, binary function, and then array. And so that's what they call an AGH array, which is like a type of fork. And that didn't work. Why not? Because we're calling this dyadically. So this will work, but when you call it dyadically, it's trying to do something extra here. So now what we need to do is we need to use this with a B1 combinator, where the binary function is the right tack, aka either pi or the K combinator, where you're discarding the left argument. So I believe this is what I call pi. Other combinatory logics call this Ki. And now when we do this, it's basically going to say, ignore this, just take this argument, and then pass it to this monadic AGH fork. So it's really like AGH B1 combinator. So this, this thing corresponds to the B1 combinator. And then, do we have a pi? We don't have a pi. Let's go get a pi. I think there's a pi here, right? Yeah, let's go steal this pi from, so this is, or, that's the Ki combinator. So we start off with pi combined with B1 and an AGH fork. And an AGH fork, I think it corresponds to like a E or sigma combinator partially applied. It's complicated. We'll just call it a fork. Anyways, we've got this. Now what's the next thing we want to do? Let's go up here and copy and paste this. We want to apply this. Which, can we do that? Can we just do this? Let's think about it. Yes, we can, because we're turning a three train, aka this AGH, into a 4 train. And when you turn a 3 train into a 4 train, what's the combinator? It's the B combinator. And therefore, this will automatically be applied. Just, you know, it's a unary function. And technically, this is also an AGH fork, so, you know, if we really want to be explicit here, you know, confusing the heck out of everyone in the chat right now, we've got an AGH, AGH, but this AGH is in parentheses, so this forms a unary function. So then we have a 4 train, which is the B combinator. Boom, and it works. And now we need to do, so now if we put the column-wise reduction here, this is gonna break because it's not what we want. What is going on here? If we put the column-wise reduction here, it's not, yeah, it definitely didn't work. But if we fold it inside this parenthesized, oop, made a mistake there. If we fold this inside here, it'll work because we're turning this 3 train into a 4 train, and then we have, you know, this is a 3 train. I don't even know how to annotate this. This is like a 3 train. Now, because we've added the plus reduction in here, we're turning this into a 4 train, and then this whole thing is a 4 train. Hope everybody's keeping up. Here, let's scroll down a little bit. And we're not even close to being done here, really. So, I mean, we're kind of close. But so now what we need to do is we've got our bit counts of the indices of our integers. And we need to check which are equal to 1. So this is where it just gets kind of goofy. I mean, if it's not already just like a mess. We need to call the B1 combinator again, do this trick, but this time we need to discard our right argument, aka we want the K combinator. So, I mean, let's just try. I don't think this is going to work at all. And also, too, this, I'm pretty sure it has to be on the right-hand side. Yeah. I mean, you can't apply the W combinator, aka flip, to another combinator. That doesn't happen. So let's try parenthesizing this B1 combinator, and then left tack. Nope. I think actually let's try and make a fork. So this is a dyadic fork, the phi1 combinator. So now if we take the left argument over here, we reprocess everything over here, and then we just go equals. That's what we want. So this is a phi1 combinator now, where all of this is the dyadic right function, which really immediately becomes a monadic function because we're discarding the left argument with this trick. And then here, we're discarding the right argument, keeping the 1 and doing equals. And so now we need to do that exact same thing again with multiplies and woo! There we go, folks. Literally, you know, this is what we call God level combinator programming. And you know, it's pretty terrible. I mean, is there a better way to do this in APL, dialog APL? I don't know. Maybe. But and actually let's put the Jello solution at the top. I mean, there's once again nothing here. And And then we go to, we were already in challenges, so then we come up here, and that's a good question. I would assume that this is going to be longer. It's only slightly longer though than the APL solution. And are we going to do BQN? Because I don't think BQN has a bits function either, and they also don't have decode, which is going to make it docs. So we need inverse decode. Oh, there we go. Yeah. Pretty brutal. Well, let's go to BQN create. And we want to go int to binary. So I mean, what were we calling? And it was what? 2, 5, 9, 11, 3, and something like that. Actually, let's do that one. And so let's call this bits, and so we want this, then we want range, and then we want bits. Oh yeah. Actually, let's just we can just change this to a 2, right? And we want it to be inverse, so can we just do there we go. Can't invert blocks. We can't, can we? I guess we call this binary decode, and we go 1, 0, 1. So that it definitely works. And I think we can make this tacit, which means that we would be able to invert it, right? So this is unary. I think we can just do this, right? Yeah. Yeah. And that means we can do inverse not found. Really? Really? That's too bad. Let's search harder on here. What if we call bit count? Bits. Binary. Binary representation of natural number. J0. Whoa. Whoa. Are you kidding? Well, this is That's bad. That's bad, folks. So we need to sum this up. I mean, we're not going to do this then, because this is not going to end up going. I mean, maybe we'll do the explicit. And so, yeah. Then there's that. Then there's that. And then there's multiplication with that. And then there's sum. So, if there happened to be a nicer way to spell this, it wouldn't be bad. And actually, yeah, what the heck? We'll do the tacit version of this. So we got that, but right, we need to do the B1 combinator. So that works. Then we need to do bits over this, which works, and then we need to do the that is not correct. I think maybe I need to put this all in parentheses. Actually, we can do nothing, right? We can indeed. And then we can do the same thing with multiplies. And then we can do sum. So, I mean, this is, how much better is that than the, I guess it's kind of unfair. It's kind of unfair because if we were to assign this bits, why is it so much worse though? I mean, I guess it's not really that much worse. You've just got one indexing, which requires 3 extra characters. And you don't have a nothing or a cap, is what Jay calls it. So you need a set of parentheses. And then we haven't assigned this. So really, this should all be, this is kind of cheating. So I don't know, let's put a footnote. Let's put a footnote here, BQN bits is I'm sure. Is there a better way? I don't know. It was on BQN crate. But the fact that you don't need the binary representation and you just need the bit count, I'm sure there's a simpler way to do this. But yeah, c'est la vie. And then yeah. Kind of sad because I like BQN so much, but clearly here Weewa, it's just. Is it just because? What happens? What happens if actually, let's commit this first. Right? Oh, whoops. And we'll add this as docs, I guess. Exploration of PWC 258 P2. So now that that's there, so imagine if we had this function. it would be that. And technically, the way it's designed, you don't even need to each it. Yeah, I guess really that's all it is. It's not that there's anything in particular that's a lot nicer. Although, well, is this easier to understand, or is the tax easier to understand? Who knows? But let's all right, let's come back. Anyways, that's our explanation of... Did we even close this? Oh yeah, we did close it. So now we can fully come back here and say this. So now we're going to move on to a completely different... I guess I haven't even started that. Project. We're 53 minutes in. We are going to go categorize. We're going to create a taxonomy for our cut functions. We're going to implement the missing ones. We're going to rename a few. And yes, so let's do that. So first things first, the easy ones. We've got filter, filter in, and filter out. So list of cuts. Filters aren't really cuts. Cuts also, let's a little background. If we go to the JNuvoc and we search for cut, there's a category of these functions, cuts, that follow this pattern. Do we have J? We've got J online. J playground. And say we've got, iota 10. There we go. And I want to cut this. And yeah, so it's usually like _1. Huh? I guess really you need oh yeah, that's what we need. Nope. So let's just create a list of ones and zeros. 1 1 0 0 1 0 1 1 0. And let's, I don't even think, do you need what the heck? What am I doing wrong here? Oh, I'm missing a dot. Uh-huh. What are these functions that I'm thinking of then? This was, I guess technically it's just prefix and infix. So these aren't cuts. Cuts are just the splits. I kind of think of sliding and chunk though. They're kind of like cuts. So yeah, I'm getting a little confused here. But let's go back to what we had. So we had, if we want to do a 2, this is what I was thinking of. So this takes, 2 adjacent elements at a time. How do I kind of want to minimize this so everyone can see. And if we change this to 3, you get 3 adjacent elements at a time. And then if you negate this, you no longer have overlapping windows. You have chunks. So, negative means chunk I guess that's not the comment. The comment is, and actually that's not going to do anything. It's NB dot. So that's a chunk. And a positive is slide. So we don't need to worry about this because we've already got all our, we turned on caps lock somehow. We've already got our chunks. We've already got our slides. So I guess those aren't in the category. So let's note that down, slides and chunks not in this category, even though I kind of think they are. But that's not what we're organizing today because those are well named and we know what they do. Coming back to this stuff, I guess, yeah, that's when you have like the maximum. Yeah, so like whenever you have a sequence of ones and zeros, and I think 2 looks at the end, right? So if I change this to 0, yeah. It's so confusing. So like the 1 looks at the first element and splits based on that. The 2 looks at the last element, splits based on that. And then the negative drops the elements you're splitting on, and the positive keeps them. So confusing. And this is just an enclosed binary operation or unary operation, but you can change this to count, right? And then that'll give you the length of each of these chunks. So these are all these cut algorithms. It's not really, filter's not really included in what J calls cuts, but we are going to call that. So we've got filter, and this is a quick, aka a higher order function. So that takes a unary predicate. Then there's filter in, takes a value and keeps. Filter out, takes a value and removes. So keep is missing. This takes a mask and a list and keeps truthy values. However, we do have keep not. I think it's currently called keep. And this takes a mask and a list and keeps non-truthy values. So let's see if we've got 101, and then we go 1, 2, 3, 4, and then we go keep. This is going to keep 2 and 4. And for some reason, turns it into 24. That's so effed up. Yeah, I don't even understand that. We'll take a look, take a look at implementation. And then there's a bunch of partitions. So what does partition do? Is it dyadic? Partition is monadic. Whoa. Whoa. So let's go check tokens part Oh, yeah, we got to look at index part 2. Oh yeah, this is one I implemented. And then there's part WTF. So let's come back here. So K. So it says partition Y after truthy indices of X. After. Okay, so this one is a dyadic function. So if it says after truthy values, I'm expecting this to group the two middle ones, which it does. Which it does. So it's kind of like partitioned in close. But instead of grouping on, it groups after. Okay. And both of these functions have the odd behavior that if you actually no part. So actually, if you give it all of these, is this also going to do one? Oh no, this. So I've implemented part wrong. So we've got part I impled wrong. This was supposed to be, APL's partition. And then part WTF is, yeah, so this, actually it's supposed to be APL's partition with the W combinator built in. And part WTF is takes two masks and splits after truthy. And then we also have IDX part. So my guess is that if I give this like a 2, whoop, didn't like that. What the heck is index part? This is G. Group the indices of Z by their corresponding values. Huh? So this is a monad? I see. So really it's a It's a key. It's what APL calls key. And then it's just discarding the keys of the key operator. And yeah. Is index part? That's a terrible name for that. Monad that groups indices by common values. And there's also group, right? Which just groups contiguous. Yeah, so then there's group, monad that groups contiguous equal values. And is there a quick for group the indices, group runs, map a link over the groups formed by identical items? Do I have this this K in my quicks? I don't. Should we add it and call it key and see what it does? So actually, let's close this, open it again, and we want equal key. It's not at all. Map a link over groups. So I don't think that's all. I don't think that is what it is all. So this, I think what this is then is it wants, it'll be the equivalent of, yeah. I don't know why this is 3. Yeah, this is 5, this is 8. Why is the 2 dropped? The 2's not dropped. Oh, I see what it's doing. Yeah. This is formed by, so this is key. Right. I was thinking this is group, but this is key. So it's looking at the identical. So there's 3 1s, 1 2, 2 4s, and 1 5. So when we go length key, it gives a 3 1 2 1. But when we go sum key, it sums the 1s, the 2s, the 8s. And so if we add a 0, we're going to get a 0 here now. And if we were to, once again, put a length, that 0 turns into a 1. I mean, so that is what APL calls key. So this is a quick, takes a unary function, applies to values of, counter. Interesting. So actually, every time we have sort group len, this could be len key. And you can see it twice here already. All right, so that's what we're doing now. That is what we are doing now. So we've added key. Now we need to go add an advisement. So anytime we have sort group len, this is going to be len key. So what is this top one? Well, actually, this one is just checking whether there's only ever duplicate values at there's only ever at most 2 duplicates of a single value is what this problem is asking for. So 1 1, 2 2, 3 3, 4. And I think it's given that you have an even number of elements. So before we did sort group len, yeah, and then the max of the lengths is less than 3. And now our algorithm advisor tells us, hey, and actually this doesn't save you anything, does it? Because sort group len is already it is still a good advisement though, because sort group len is much shorter. But then this is where it's going to be crazy. So if we add an advisement that is sort group, and then it's going to be a monadic function each. This could be that monadic function key. Now that is freaking fire. That's 4 atoms down to 2. That's the best advisement we have, folks. So for example, instead of doing, so we have the specialization of group length, so it works, but say instead of doing group len, we wanted to do the sum. So we now have to just group and then go sum each. But now if we reload this with the advisement, it's going to tell us sort group sum each can be replaced with sum key. Holy smokes, folks. Look at that. Look at that. 24645. 24645, folks. That's have a good night, C4Tubo, if you haven't already signed off. This is awesome though. So let's commit this. Add key and advisements for, sort, group, etc. That was highlighted the stream so far. So we've got I'm not signing off. I was just saying goodbye to C4Tubo, who he said he was packing it in for the night. So what's missing here? I mean, technically we're missing a higher order or a quick called group by, which is the generalization of group that takes and keep is missing too. So actually let's just group by, which is group by is missing. It's a quick, takes a binary predicate. Paul asks, if you've got to add an algorithm library to a language, would you add the 120 functions from the STL? No, probably not. I mean, a lot of them are super useful, but I would probably start with like what I think are the fundamental ones. A quick is just what Jello calls a higher order function, which maybe I should change, but so we're missing. Let's get a little. What's going on here? Let's go back here. Let's come over here. Let's get this little yellow thing. So keep is missing. Group by is missing. And we should. So first thing we should do is we should rename. We should rename keep not. We should rename part WTF to partition after. And the index part isn't really it's really like a I mean, what does index key do? Not what I expect, but that's kind of what this is. So yeah, we've got this. So index part. But what if we do index yeah, but so the difference is that it's like the index from before, so it's kind of like it's almost like a key original index, you know? Yeah. So we should rename this to part after. So we've got filters, keeps, and groups. So maybe we should implement keep. We should implement group by. We don't even need group right now. We could just kick that down the road. I definitely need to implement keep. And then we need to rename everything here. So let's do the renames first. So, because that's easy enough. And actually, let's check. Are my tests still working? I never run the tests. Yeah, look at that. They're all still working. So let's change index part to key index. There's that. And now we can actually, let's... Actually, we should put this all on a table, shouldn't we? Guess we can turn this into, do we have docs? Do we have a docs folder? We don't have a docs folder. We will, at the end of the day, turn this into a docs/cuts.md. The name cut is borrowed from J. Cut. And keyword type arguments description. Whoops. I guess, yeah, it wants more of these. Yeah, we gotta go fix it. This is a dyad. This is a actually, it can be just any array, I guess. This will be a Forgot the new line. Thank you. Keep not. So we got to go change the name of keep to, oops. Oops. So we can remove this now. Removes. Falsy values. So yeah, this is broken as well. So this should be a monad. Takes one list. Partitions on. Values less than 1. Many of these names seem not obvious. Yeah, it's kind of a mishmash. Filter is, I think, pretty agreed upon. Keep is stolen from Weewa, although other languages call it compress or replicate. But I kind of like keep. Partition is part is short for partition. There isn't unanimous agreement about this. It means something different in C++, but it it's what it's called in the array languages, at least APL. So part we need to rename to part after. So it was originally part WTF. This is now part after. And this takes two lists and partitions on mask after truthy values, and it is a dyad. Group is pretty simple. Monad list groups contiguous equal values. Group by doesn't exist, but it is a quick binary predicate. Groups based on satisfying pred, and then key index is a monad that groups I don't want to use the word groups. It, key groups indices. And then this is a quick. It takes a unary fun and applies fun to values of key. This is really, I guess I can put key, counter here, which is what it's called in Python. So let's go commit the renamings. So I just kind of reformatted this. Just to clarify, I collect values that are the same and perform some kind of reduction on them. Like the length of the set. Yes, except length is technically a unary function, not a reduction. It could be implemented in terms of a reduction. But yes, your understanding is correct. So we're going to call this recycle rename some keywords. Of course, I don't know what I'm doing here. And we will push this. All right, next thing is that we need to implement at least keep and fix part. Let's see if we can fix part first. So what's the problem? With parts. So this works kind of. We don't want that trailing 0 there. And also, if we only have 1s, then we get back this integer, which we definitely don't want. So let's go partition. So if x is greater than 0, wonder if does this simple fix work? No. Well, because clearly, so I'm just thinking in my head here, but clearly when I created this, I just copied group equal and modified it a bit. But it's not working. Um, Yeah, I see what I... I mean, why just not skip all this garbage, you know? Filter. Does that work? It did not. It actually did. Right, because whenever you do these split things, if they only have one, it doesn't turn it into a list. Huh. So what if I do that 0, it still works? Well, I apologize for the silence. I mean, but sometimes you just need to think about something and it works. That is quite nice. Fix, so this is a bug. Fix, I mean, there's still an argument that we should rename this and create a more generic part. So we can come back here. Part is now fixed. So now we need to implement keep. And keep, it's flattened, so it's actually really simple. Mask array result equals this. I mean, we can even just return it in a list comprehension, right? Value for value m in zip array.mask if m. And we need to figure out what this will be. And we call this keep xy. And because this is dyadic, we can just use k underdot. Go back here, do that. This would be pretty remarkable if this worked in one shot. Come back here, now we need to go to Jello. And where is keep not? Right there. So we put keep underneath it. Use k underdot. And I mean, wow, look at that, folks. Freaking fantastic. So, I mean, we'll come and commit that in a sec, but let's go back to we want to come back to this right here, where we have this index at index. So this is PWC 251, 250p1. Yeah, so this was, oops. Yeah, you're definitely right, Stuart. There is a group by in the itertools library, and at some point, you know, maybe in the future, I will go back and go through and refactor a bunch, because there's no reason we need to hand roll that, but I didn't write that original code. So if we go 3 3 3 3 and we do this, the result should be 3. And now if we just go keep, oh, I need a dyadic separator though now. Haha, let's go. And so now, if I go so that we get 13, this should be 2 3s. And then that's why we need the head. Well, let's go, folks. All right, so first things, we also got to add this to the README. This is was keep and bqns/apls compress /replicate. And also I think actually I have a missing atoms. So we did Q's prior and was keep. So we are going to say that this this is a sparkles for sure. Add not closes, but address is part of that. Push this, come back here, git diff this. Ooh, we didn't want that. And actually, let's do this all at once. So, this is our new solution. Ooh, and then I think, whoa, that's not what I wanted to do. So now, because we push this, we can click that. And yeah, because I did some investigation on my own. Index : at index. So I think all of these really I don't know. Do we want to add? We definitely want to add one of those, right? To the algorithm advisor. So let's go here. So this is index : at index. And this can be replaced with colon keep, I think. So now come back here. Yeah, now we do this. And if we get rid of this, yeah. So we got that. Take this. And we want to go back to our challenges. Do that. We also have to replace this with that. And also, we forgot, oh, we'll update that separately. So yeah, this is closes this. And addresses, I guess I didn't do this for the last one, but oh well. The thing I was meant to do was that this can be length key, and this can be length key, and then I guess also we need to copy and paste this. I guess this is a recycle. So this one should have got mentioned here. Yep. And then this one should have been closed. And then if we come back to our cuts, and we still need to implement this one, but I don't want to do that right now, so I will punt that down the road. We don't even need to explain. Yeah, we still need to think about part, but we need the last one though. I mean, this one's basically done now. Keeps, filters, splits, partitions. Is there splits that we didn't look at? Yeah, not really. These are fine. Which means if we go back to the top of this file, we just did that, minus group by, we just did that. And I said we were hoping to finish all 4 of those in 2 to 3 hours. It's been 2 hours and 9 minutes. And that means we're going to do this next, which is going to be super exciting. I need some more tea, so I'm going to take a quick break. And I'll be back. Don't know. Also, should I try turning on does that shed anymore? Holy smokes, that is way brighter. I don't know why I didn't have that light on before. Working in the dark. All right, we have my glorious tea. Paul asks, what are the most fundamental set of algorithms to build on? Reduce, map, filter, chunk by, adjacent filter, and more. But yeah, I'd start there. Reversals, permutations, compactions. And then everything else would just be implemented in terms of those. All right, now is going to be the most exciting part of the stream for those that have either just tuned in or stuck around. We are, and actually, you know what we should do? Let's go commit. Let's create a new folder, move the to-dos there, and preview of cuts. And let's just go commit this. Cut doc. And now we are implementing. If we go back to our issues, we are now, oh yeah, and we can close this basically. Group by needs to be re-implemented, needs to be implemented, not re-implemented. But this is basically done. And so now if we go back to issues, we're going to work on a part of this, and that is this. So this was suggested by Andrea Cortis, and they asked for something where basically if you provide an input and an output, or two inputs and one output, could you match the functions to the inputs and outputs? And I love this idea. It actually already exists in a language called Pharo. I don't have it on my computer right now, so I can't really demo it, but we're going to build it up. So this is, oh yeah, scan, of course, is one of them as well. Paul mentions fundamental algorithms. This is going to be, if we get this working, if we get this working right here, it's going to be super exciting. So first things first, if you hit question mark, you can get a explanation of combinators. So now we want something like dash dash find by example. And then in the future, we'll also have find by, signature, something like that. So let's go find the piece of code. So yeah, if we input, if this does this, then it skips over to this explanation and continue. So basically, we're going to want something similar to this. If equals dash dash find by example, and actually we should just like commands equals a list of dash dash find by example. And then go commands. And then we come back down here. And then if, I mean, where does this, why am I doing this strip 17 times? Can we just do a strip at the end here? Seems like it. Yep. All right, so that works. And now run jelly. So let's just say find by example. So can we do input in the middle of this? Print x equals input in out x dot split okay. And actually we should put this in parentheses because it's optional. So 3, 2. Wah-ha! Wah-wah-ha! Man, this is going to be exciting. We might factor this out into a so it's just run jelly. Yeah, so really it should be input, arguments, and desired result. And then if len of args is greater than 3, print 2. There are too many inputs. Max is 3. L if len args equals 2, print dyadic find by example not supported yet. So we go 3222, too many inputs. Then we go 322. What's X? It's actually should be 3 here, and this should be args. 322. Ooh. And then we go 32. List object, because we already split it. All right. And the next thing we do is we get rid of this to do, and we don't even need to convert our expression. All we need to do is go for monad in tokens dot monadic run jelly with monad and then args and print this. Whew, this is going to be exciting, folks. This is going to be exciting, folks. All right, let's clear the screen. Let's clear the screen. I'm guessing this is going to crash and burn. But you never know. You never know. That's what we expected. That is what we expected. So now we're going to go try except continue. Just ignore the errors. And x equals, and then let's print f string and you know, like arg0 space arg1 and then x. Actually, that's totally incorrect. That's totally incorrect. Totally incorrect. So when we get to here, we should destructure this. So in, or what do we put? Arg out equals args. And then really we just want arg here. And then we'll just currently print x. Yeah, we'll just do that for now. And yeah. Well, why are we printing? Run jelly. I see. So let's display error equals true. If display error like that. And actually, we do want to raise whatever the exception was, don't we? Else raise E. Ooh, it's kind of terrible what I'm doing, but you know what? Whatever, it's fine. That didn't work at all. Yeah, I guess this calls a draw function, which I just realized. Not very functional. And also, do we need the right, and we didn't even set that. Silly goose. Whew, there we go, folks. Now we're laughing. Now we're laughing. So these all return none because we're not returning anything from this function. So we don't actually want this to be. This is really terrible what I'm doing. Don't do this at home. Like, this is terrible, but we're just hacking. So if display, and actually let's get rid of this default value. And output text. Do we need to return? This would fail a bunch of MyPy typing stuff, but that's okay. And now this will actually, in the X here, show the results. So let's do that again. Find by example, 3, 2. Well, first of all, we forgot that we need to add. And I think that's the other error because we don't have the right thing there. 3, 2. Ho, ho, ho. Oh, baby. Oh, you think raise on its own will do that? Arg monad. So why does sub 1? Ooh, is it because it's a woo? It does show a 3. So what? Yeah, so I can't clear this, but if I go, well, it's going to clear anyway. So if I go 3 sub 1, display. This should be 2. So what is the problem here? Pretty simple, hopefully. Converted expression. I think it's supposed to be a list, maybe. So if that's the case, let's just put this in a list. Nope. No, scan is definitely a building block. Well, okay, let's just debug right before we call this. If we go print that and print that. Okay. So it does actually seem like it wants print monad, print arg. Ooh, it's, I see. There's your problem right there. Is this it? Is this it? Where's sub 1? What the fudge? Well, let's. Oh. Dot values. That's a huge mistake. And then I think it is this. Well, let's just try it without. Ooh. So we want to go items, and then we want to go keyword atom. Actually, I think we're done with this now. Run atom, but display keyword. There we go, folks. That's exactly what we want right there. And so now is the moment of truth where we go if x equals out. Look at this, folks. Look at this. Oh my God. Whew. As predicted, we've only got a single level of nesting, but what did we want to see? We wanted to see bits, and we wanted to see sub 1. Okay. All right, folks. Whew. We're just getting started. We're just getting started. So now what we want, oh my God, this is going to be so cool. This is going to be so cool. So now what we want is every single, we want a power set up to a number of monadic glyphs. Like, because we could just create some kind of nested for loop, but that's silly. I mean, we can do it just temporarily. Just temporarily. And actually, that'll ignore... That will ignore... So this is super hacky, and we're going to refactor this in a second. Single atom and 2 atoms. And we'll call this keyword 2, atom 2. And we're going to go atom plus atom 2. And then we're going to go keyword 2. And now we're going to run this. And this stuff needs to be tabbed in. And let's reset this at the top. Find by example. 3, 2. Interesting that the random element showed up this time and not last time. Oh boy. Oh boy. Ladies and gentlemen, we have just created a program that writes its own code. And there it is, folks. This is interesting. Any functions that act as identity functions when they don't work, when combined with something that actually produces the right answer, interesting. So we're going to have to filter all these out. But this... What was the third one we wanted? Right there. Right there. Tail pop. Interesting. All equal double. All equal add 1. Any double. So anything that adds in 2. Anything where you ask it to end in 2. Is going to generate a bunch of results. Well, really what we should do here then I can't escape. I can't escape. We need to put a parrot. We need to go to Jello. I mean, clearly anything more than 3 is, it's already 2 is taking forever. So really, we're not going to do anything super fancy here. we'll continue. If x equals out, else. Run atom plus atom 2. And if it crashes, then we do that. And yeah, next time we do this, let's choose, so 3 in bits gives us 2. 5 in bits gives us 2. What is actually, let's just do it this way. 10 gives us 2. I guess, yeah, it's 8 plus 2. So 11 gives us 3, 12 gives us 4. Right, 8 plus 4. 31 gives us 5, right? So let's just do that. 31, 5. But now we're not going to get sub 1, obviously. Well, that is, what do they call it? TDQM? How is double sub 1, 5? All right, let's kill this again. So let's go to ChatGPT for a sec. We haven't done any ChatGPT programming. Gotta log in first. All right. I have the following code. I want to not just test every atom, but every atom and every combination of two atoms, i.e. atom plus atom 2. Is there a power set or combinations function in Python itertools I can use for this? Atom is a string. I mean, it's kind of what I want. So I wonder if you can do that kind of dictionary literal addition. this kind of literal Okay. Now I want to parallelize this across 64 processes. Can you please do that for me? Is that Stuart saying combinations will not give all orderings? Yeah, we'll do that in a sec. All right, all right. I don't actually think this is what I want, but how does partial work? I can't even remember. Is it? Should we test? Do we test that? Partial. Yeah, screw it. Well, we could ask ChatGPT to do it, but All right, let's crash it. If I want is to pass in arg and out as the two combinations and use partial func tools, come back. It has to be at the back? $31. Something. Well, something's definitely not right here. Well, first of all, someone told me that combinations doesn't do combinations, or doesn't do what I want. I want permutations. I need both combinations and permutations? What the? Why? Also, Jesus Christ. What the fuck is going on here? is it possible that actually, yeah, let's print out. Something seriously is going wrong here. Okay, I mean, that's accurate. So we don't need this plus here. I mean, let's do this. Ha ha ha. Print run jelly atom1 arg display false. Like, how is factorial sub 1? What is going on here? Is it that I got rid of... Is that it? I mean, this looks more accurate now. And we got the individual one. So I think that was it. So really what we need to do is we need to filter in the monadic case. In the monadic case, because that's the thing is, in Jelly, too many of these operations, when they fail, they just treat it as the identity, right? So what we need to do is if atom1 equals this, continue. Else if x equals out, continue. Right, so it's going to skip. I mean, you're doing multiple processing now, so I mean, it's times 64 cores, so what? This did not work at all. I don't understand. I mean, this one's definitely valid. This one's definitely valid. Like we should never see. I mean, how is absolute value getting through? Ah. I'm an idiot. I'm an idiot. indentation error. Right. So here we go. 31.5. Okay, we also need to kill so technically it wasn't wrong what I had. Wasn't what I was trying to do, but we also need both of those. Oh, wait. And what is 30 bits is 4, right? Let's do that instead. 34. So we want to get rid of random elements. Well, this is running. Let's go figure out how do we get rid of a key from a key the can I do it in a single it's brutal. So we've got this. Let's comment out this. Yeah. All right, thank you. Yeah, CPU does go burr. You can see, though, this isn't optimal because at the beginning, all of my cores were lit up. But I think there are some extremely computationally expensive... Oh, wow, yeah, look. I'm maxing out my... memory's being throttled. I'm using all 32 gigs. Well, let's try something. Let's half this. I see it just explodes at some point here. It just went from like 12 gigs and now it's going to max out at 30. So there's some kind of concatenation of these operations that absolutely just wreck the memory. Oh, and interesting, you can actually see, isn't that cool? You can actually see, I mean, OEP, that's almost definitely got to be like permutations, right? An OE exclamation mark. OE, yeah, power set. Yeah, no kidding. So let's just get rid. And what is the OE exclamation mark? All permutations. Yeah, that would do it indeed. So let's go get rid of those as well. I'm pretty sure I call them power set and perm. But let's go confirm. Yeah, perm and power set and perm WR. Let's get rid of that one as well. Where are we going? We're going over here, back to Jello. Whoops. Actually, that's not what we wanted, is it? We wanted 30 and 4. It's still unbalanced though. Like you can see that very few of my cores are lit up now because the way that that's why I said I wasn't a big fan of what was happening here. It's basically just chunking this up based on the number of processes you have and then dividing up the work like that instead of queuing everything up and then having some kind of queuing algorithm that dishes things out to the cores when they're available. Because we basically were multi-threaded for, well, I guess actually we were only using 32 of our cores, but still. Yeah, that's true, Stuart. I mean, already we're doing we already did what Pharaoh did. Find by example in Pharaoh doesn't test combinations of functions. It only tests single functions. So maybe what we should be doing is just going back to what we got working in like 20 minutes, which is just the single function test. And yeah, look at this. Yeah, we're down to a single core. I mean, this does work though. Half of 30 is 15, and then the length of the divisors is 1, 3, 5, 15. Yeah, I mean, this stuff does work. Can't believe this is hanging on one core. What is this? Actually, let's look at what's taking so long again. Where is its exclamation mark T? Let's go take a look, folks, and get rid of it. Exclamation mark. Where's exclamation mark? Am I blind? Where's T underdot? T underdot's here. That's fine. Where's exclamation mark? Actually, let's just do the lookup in my tokens file. Factorial. That makes sense because you're doing 31 factorial and then a bunch of stuff on it. So let's. I don't really want to get rid of factorial, but we can go and fix it later, right? We can go and fix it later. And let's call this something else. Excluded keys. Find by example. So what if we do now 3, 2 again? And actually, what if we do 64 cores again? Look at that, folks. Look at that. Factorial took forever because we were calling it on a large integer. And then that by itself is probably takes a certain amount of time. But then on top of that, if you are calling like iota or range on 31 factorial, that's going to allocate a ridiculous amount of storage space. So how many we're down to what? 1 core? Look at that, we're done. That wasn't too bad if you've got a machine with 32 cores. I mean, we can speed it up, obviously. But yeah, sub 1 bits. And I to B, sum vec. These were basically everything that I wanted. And now if we do it again, but with, 31 and 5, you're going to get way fewer results. And what is this weird looking E? Yeah, this one as well. Compute the array of exponents of z's prime factorization. That doesn't seem that bad. AED. Divisor count. Yeah, I mean these ones take a little bit more time. For the amount of time that takes, I definitely do think, though, that it'd just be more valuable to have it work on like one level. All right, what do you think? We really need to set up formatting too. Git add, git commit. Initial start of this. So edit to do. We need to add support for dyadic functions. Add input to ask one or two functions. And this is the important one right here. Initial work. Oh yeah. Add input to ask how many cores. 64 by default, because And yeah, in general, fix algorithm for chunking / distributing across cores. Maybe use IMAP or something else. What is this issue? Well, let's spend 2 seconds looking at this. Actually, no, what we wanted to do first is yeah. All right, we gotta go fix some stuff. 116, 120, 122. Looks nicer. 120. Oh. And all right, now let's go look at last but not least. What is this? I think someone commented on this too, that or made a comment on the video that I could just use logarithm, but yeah, let's do that. What is star? Exponentiation with base x. Oh, I see. It's just this that's happening. It's just 10 square. What is it? It's 2 to the power of 10. 3 to the power of 10. Yeah, that's all it is. I mean, it'll be fixed once we clean up what this shows, right? So why did I guess I was just confused when I set this up. This works fine. It just looks weird when the is applied without the right argument 3 will be hidden. I think I have an issue for this. Yeah, enhanced trace skipping. Make sure to skip dyadic functions that have a actually edit. See here. Well, actually. Close this, close this. Actually, wait, I needed that. Enhanced trace skipping. And actually, we linked the wrong one, didn't we? This goes here. And then this goes to itself. Right, we were supposed to close that with comment, but oops. All right, we went from 18 issues to 13 issues. And if we come back to this Jello repo, we got everything done. I mean, this is only kind of partially supported, but the initial work works. So that's where we're going to end it. It's 9 p.m. local time. Hope everyone has a good night or good day, depending on where you are in the world. Thanks for tuning in, and we will see you in the next live stream.